This webcast discusses how to complete the lab report for the Tumble Buggies lab. So we have already done quite a few things in class. I may cover some of the same ground, but I'm just going to go from the beginning to the end of the lab report and talk about how to finish it. So first of all, anywhere there is blue italicized text, that is an indication to you that you should be inputting information there. And I wish you would replace the blue text with black. So like if you typed your name here, and I'm just making up a name, and then you can just change this text color to black. And that way you'll note that you have put information in that spot. Okay, so wherever you see blue italicized, that's kind of an indication of an action for you. Okay, so we made observations in class as we watched the buggy move across the floor. And then we talked about if we want to study the motion of the buggy, what would we want to measure and how would we measure it? And then we identified our independent and dependent variables, and we put our constants in. Please make sure, double check your constants. Don't just tell me that, for example, that the buggy always began at the same starting position. You have to be specific. What was the value of that constant? So here, in the example I'm using, the buggy started at position 600 centimeters for all trials. And give me the specific buggy number that you used, and be specific in what direction that the buggy traveled during each of the trials. Okay, so, but we did discuss these constants in class. Okay, the next section is the results. So this is where we put our measurement data. Now my table is not complete. Yours should be complete. But I did put some values here because I want to show you how to do something at the bottom of the table. Okay, so notice that in our data table, we intentionally chose levels of the final position. This was our independent variable. And then we measured the dependent variable, which was the time that it took the buggy to reach that position. Okay? And then we need to calculate the average amount of time. Let's see, I've calculated this here. So that would be, okay. Since we have a calculated field, we need to show a sample calculation. Now, we only need to show a sample. We're just going to do this for the first row of the data table. The reason we're doing this is that we want to be totally transparent and clear about how we did everything in our experiment. We're hoping that other people might replicate our experiment. It would lend a lot of support to our results if other people got similar results. Okay, so let's delete all of this blue italicized stuff. Okay, we want to use the equation editor here. The equation editor is a really nice tool inside Microsoft Word. It's actually inside all of the Microsoft products, and it's very useful when you are doing something related to math or science so that you can show equations and things in good notation. To do this, I'm going to insert. So I'm going up to the Insert tab at the top of the page, and over on the right, we can insert equations. So I'm clicking that drop-down list, and it does give some sample equations, but they're not really the kind of equations you need right now. So we're just going to insert a new equation. I click that, and it gives me this box, which is where I can start typing my equation. Okay, so I click in that box. I'm going to say the average equals, okay, the average is just adding up our measurements and dividing by 5, right? Because that's the number of measurements we had. So I'm going to have a list of numbers in the numerator, the measurements that I added up. I need to put that list inside parentheses so that this tool understands what is in the numerator, okay? So I'm going to put my list of measurements, 3.75 plus 3.66 plus 3.81 plus 3.76 plus 3.69. Okay, so, and then I close the parentheses. That is a list of the 5 measurements that we made in the first row of the table. Then I say divide by, and since my denominator is just a single number, I really don't need to put that in parentheses. Okay, here is where the magic happens. Hit the space bar. When you hit the space bar, this equation editor reformats that into the form of a fraction. Okay, so that's very nice. This is a very nice way of depicting what we did. It does not calculate it for you, so I have to have calculated it, but then I'll say equals 3.73, keep 2 decimal places, and put seconds, put a unit on it. Okay, so this is the sample calculation. We only need one of them. We need to do this for the top row of the table. Okay, after our results in this data table, we want to put the graph of our scatter plot. We made this on paper in this, let's see, there we go. We made this graph on paper, and so you're going to need to take a photo of it using your computer or your phone, and then we're going to insert it. I'm going to just go to a view of multiple pages so you can see where the graph goes. Now I don't want to leave this blue italicized text. That was just a reminder, right? So I deleted that, and now I'm going to insert the graph that I have snipped. I want to make sure that this graph is sized, you know, basically the full width of my page. Okay. Okay, so now that graph is inserted. It's properly labeled. I can see the title. I can see both of the axes labels and everything like that. So this looks good. Then we'll go to the next page. And I'm going to delete these blank lines. We don't need all of those. Okay, now we're going to the analysis section. Now this is a very short section. There's no real writing of text, but we're going to show a lot of important information. We're going to show the detailed calculation of our slope. Okay, so we used this graph, and I've identified 2 points on the line of best fit. I marked those with triangles, and then I have labeled the coordinates of those 2 points indicated by the triangles. I need to show that I've used these coordinates to calculate the slope. Okay, and I'm going to insert a new text box. So I'm going to insert at the top tab. I put a new equation. And I'm going to put the numbers in the numerator on top. So 480 minus, let's see, what was that? 480 minus 400, and 6 minus 9.2. Okay, so 480 minus 400, that was my y2 minus y1. I put it in parentheses, and I say divide by. Now in this case, I do need parentheses around the things in my denominator because it's more than one number. And that was, no, I forget again, 6 minus 9.2. There we go. 6 minus 9.2. When I hit the space bar, it reformats it as a fraction. I'm going to say equal. Let me do that math. And I get 25 centimeters per second. After I type centimeters/second, if I hit the space bar, it makes my units, it orients them very prettily as well. Okay. For the y-intercept, I really don't need a equation box for this. I can just type it. Oh, I think it was 600. Okay. Then we're going to give the physics equation. So I have identified my independent and dependent variables and the names, the descriptive names that I'm going to use for those in my equation. Okay, let's insert a new equation. So I went to insert on the top row, I go to insert new equation, and I'm going to put my physics equation here. So the dependent variable I'm calling x. So x equals, I want to put my slope in parentheses, right? So 25 space centimeters slash second space, so that it orients those units as a fraction. Close the parentheses, hit the space bar, and that makes it look pretty. And then I'm going to put t, and then I add my y-intercept and put units on the y-intercept. Okay, so there's a good physics equation, right? I followed all the rules. I used descriptive names on my dependent and independent variables. I put the slope in parentheses, and I put units on both the slope and the y-intercept. Okay, so that's a good equation. That's the end of the analysis section. Now we are to the conclusions. And there's a note here. It says be sure to double space. Okay, so I'm going to delete that. And let's go up. If you don't know how to double space in Word, you go to the paragraph. Oh, I'm on the Home tab, but there's a paragraph set of tools here. And one of them looks like this with the up-down arrows. And I'm going to choose a spacing of 2. Okay? And I'm also going to change my font type color to black. Okay, so, and we're going to indent our paragraphs. Oh, I don't want the underline and the bold. Let me turn those off. Okay, so I'm typing a tab to indent my paragraph, and the first paragraph needs to say something about the purpose of the lab. So the purpose of this lab was, and this the objective of this lab was actually given on the first page. It's right here. It says determine the relationship between the position of the tumble buggy and the amount of time that it runs. Hey, I can just copy that down here. Was 2, and let me just paste that in. And I might need to change my D to lowercase. But look, there's my purpose. Okay, I have satisfied the requirements for this paragraph, and so I'm finished with it. I know it's a very short paragraph, but that's okay. In science writing, you want to be concise, meaning, don't be wordy. Use as few words as are possible to give a clear message, okay? But in addition to being concise, we need to be accurate, and we want to avoid ambiguity. When we say things, we want them to be able to be interpreted only one way, in the correct way, okay? Okay, so it's okay to have a paragraph that's only one sentence if it fulfilled the reason that you needed that paragraph, okay? So the next paragraph of every lab report should briefly summarize your results, okay? So I'm going to start here with a one sentence that describes the key constants, the constants that would differentiate Team 1 from Team 2 from Team 3. And I think those are the buggy number, the starting position, and the direction that the buggy moved. So I'm going to say, in all trials, buggy number 2 started at an initial position of 600 centimeters and moved in the negative direction. Okay, that sentence just very quickly summarizes the key constants in this experiment. Now I want to describe the scatter plot, right? The plot of our data. And I'm looking back at it here, and I see that the trend was linear. So I want to say that. Oh, and I also need to kind of give the name of the graph. Okay, so I'm going to say the position versus time graph for the buggy was linear. right? That will tell anyone who's reading this. Everyone has a good sense of what we mean by linear, okay? And the equation of motion is shown below, or is as follows, or something like that. Okay, so I'm going to put in my physics equation here. Type a return so you're on a new line, because physics equations, or any equation, should always be on their own line and they should be centered. Now, we've already taken the trouble to make a beautiful physics equation in the equation editor. I'm just going to go up there and copy that and then come down to this line and paste it in. Okay. Notice that as long as the equation is the only thing on the line, Word will center it. And that's what we want to do. All equations should be centered and on their own line. Okay. Now I'm going to continue, and this is part of the same paragraph, so don't indent here. Okay. We've given the physics equation. Now we should explain what we know about this equation. And so as I'm reading this equation, the first thing I see is the slope, okay? So let's say the slope of 25 centimeters per second means that for every additional 1 second that the buggy moved, its position in, here it decreased. Why do I have... I'm so sorry, girls. My slope should have been negative because I'm doing an example where it moved in the negative direction. And this 6 minus 9.2 would have been negative. I just overlooked that. Okay, so let me put my negatives in because it is a negative slope. And so in this case, the position decreased, right? The position got smaller. The graph had a negative slope. It decreased by 25 centimeters. So for every additional 1 second that the buggy moved, its position decreased by 25 centimeters. Okay, I can also, I think, explain the y-intercept here. The y-intercept of 600 centimeters was the initial position of the buggy in all trials. Okay, so we're able to explain both of those numbers. Okay, notice I did not indent these two sentences because these are a continuation of that second paragraph. But now I'm going to a third paragraph, so I'm indenting. When we were observing the buggy, we said that we thought it was moving at a constant speed. And now I think we have some evidence that supports that. And so I want to explain that. That's kind of one of my conclusions here. So the slope of the buggy's position versus time graph was constant since the graph was linear, right? I mean, the slope did not change anywhere along that graph. The slope of the position versus time graph equals the velocity. Since the slope did not change, buggy number 2 was moving at a constant velocity. Okay, so we've given the evidence that we found that supports that observation. In the observation, we said it seemed to move at a constant velocity. Well, now we know that it did. Okay, and then the last paragraph of the conclusions, we need to think about how we measured and got our data for this experiment, and were there any errors that and maybe ways we could improve on this if we wanted to replicate the experiment, to repeat it, to confirm our conclusions. Okay, there are always measurement errors, and by saying that, I don't mean that we were sloppy or not careful in the way we measured, but you know, just the nature of things is that there is always an error in making measurements. So in our particular case, I think the largest source of measurement error was related to using stopwatches to measure the time that the buggy was moving. So let's explain that in a little more detail. The timer, or let's see, how do we want to word it? The timer had a reaction time. Oh no, I don't like that wording. Let's say there was a human reaction time, both when the timer started the stopwatch on hearing the word go, and also when the timer stopped the stopwatch on seeing the buggy pass the final position. Okay, so there's a human reaction time error on both sides of our measurement. Now, if this were a very important experiment, we would actually work hard to measure this error. But for right now, we're going to quantify it. We're going to try to put a magnitude on it. And this is just our best estimate, okay? So if we thought, could this error be as big as 10 seconds? No, I don't think so, right? I mean, that's a lot of time, 10 seconds. Could it be as big as 5 seconds? No, that seems too big too. You know, if I think about it, I think that maybe this error is on the order of half a second. And it's a random error. Sometimes our measurements are too long and sometimes our measurements are too short. Okay, so I'm going to say we estimate this time measurement error to be approximately, and I'm going to say plus or minus, right, because it's a random error. Sometimes we measure too much, sometimes too small, and I'm going to say half of a second. So plus or minus half of a second. Okay, now that we've described the error and we've tried to quantify it, to put a number to it, now let's think about, if we did this experiment again, what could we do to try to reduce that error? Now, it would be really nice to maybe have better equipment, but I don't think that we have the money to go buy a more complex time measurement system. So we're probably stuck with stopwatches, and that means there are always going to be human reaction time errors. But we could still do something to reduce those errors. The more trials that we run, the more measurements we have. When we average those together, since some are too large and some are too small, so some are positive, some are negative, in other words, the average of those errors tends to move towards zero. Okay, so in order to minimize the time measurement error using stopwatches, it is recommended to have at least 2 timers and to conduct a larger number of trials. So that way, instead of getting 5 measurements, we might, if we did 10 trials and we had 2 timers, that would be 20 measurements, okay? So it would really increase the number of measurements that we had. Having a larger number of measurements would tend to make the averaged effect of this error be smaller. Okay, So that is the conclusions for Tumble Buggy.